All right, so welcome back, guys. So in this video, we're going to go over tons of example how to find the antiderivative of a given function. How do we know what to do? Usually the instructions or the direction on these type of problems in this lesson is say that usually we're given some sort of integrals and it will ask evaluate the following indefinite integrals, or it will be in this form where you have the integral notation and you have some function inside and this dx. So when you see something like that, you ask to find, okay, what is the antiderivative of the function inside the integral? So in other words, if we want to understand what this is saying, that we want to find, so this means we want to find what is the function that we take the derivative and get 2. Okay, what is that function that normally when we take the derivative and we get 2? Well, we've done tons of those functions, and I think the one that we're thinking about right now is 2x, right? So if this is the given function, then when we differentiate that, d dx of this is 2, right? So the reverse process of this is I'm sorry, let me go back. Oh, that's not that one. So the reverse process of going from 2 to there is anti-differentiate. So that's what we're trying to do in this lesson, is that given a function, can we find what was the function before that? When we differentiate using certain rule of derivatives, we get 2. Okay, so in this case here, so let me just write this down here. So if we had the integral of 2 times dx, then a function that we try and find the antiderivative of is 2. Well, we know that's 2x. So the answer for this here is just 2x. But is it really just 2x, or is it 2x plus some constant or plus some number? Well, it turns out more than just 2x, because 2x is just one of the antiderivatives. So recall that the indefinite integral itself, this here, is equal to this, and this represent the family of all infinite many antiderivatives of a given function. So 2x plus some constant c is the correct answer for this problem. That is the answer for this indefinite integral of 2 times dx. So that's it. That's what we're supposed to do when we ask to find evaluate the following indefinite integral. Is given integral, or our goal is, hey, what is the function that we take the derivative and give us 2? Well, that's 2x, but there's more than just 2x. It could be, for example, it could be 2x plus 5, or 2x plus pi, or 2x plus e, or 2x minus 7, something like that. So infinitely many, right? So to capture that, we just say, okay, well, it's going to be different by some constant c. All right, so moving on to the next example. The integral of 16 times e to the t dt. Okay, so this is indefinite integral, and the function inside we have is e to the t. The variable is t. Now notice that there's a constant in front of e to the t there. So again, we try to figure out what function. Okay, what is the function that when we differentiate that, we get e to the t? Well, isn't that just e to the t itself? Well, what about the 16, right? So it turns out there is a rule, right? There is the rule that we can use in this case, just like when we differentiate a function. If there's a coefficient, we can just leave the coefficient there and times that coefficient to the result of the answer. So very similar here. That 16 can be pull out or just move out in front of the integral, and all we have to do is focus on find the antiderivative of e to the t. Well, in this case, the antiderivative of e to the t is just going to be e to the t plus some constant c, but that will give us 16 e to the t plus 16 times c. Now, you may ask, what the hell is 16 times c? Well, c represents some sort of constant that, could be any number. So when we take 16 times c, the result is still going to be a number. So our answer is going to be 16 e to the t plus a bigger c, for example. Whatever that result of 16 times c is. Okay, it's just another number. So this here is the antiderivative of functions. We say function because of 16e to the t, because it's not just a single function, it's infinitely many functions. All right, so next we have, let's do this one next, part C. What is the integral of 3x to the 4th times dx? Okay, well, let's use the previous result here to kind of factor out that 3 or move that 3 out first, and then just focus on figure out what is the antiderivative of x to the 4th. Well, we're thinking, okay, what function such that when I take the derivative, I get x to the 4th. Okay, well, we know that function we're thinking of is, well, to get the derivative to be x to the 4th or the 4th power, we know that function has to have a 5th powers, because when we differentiate a polynomial using the power rule, we bring down the power, right, and then we subtract the power by 1. So it has to have x to the 5th, but okay, well, how x to the 5th, but this is just x to the 4th. So when we bring down the phi and subtract by 1, we get phi x to the 4, but we want x to the 4. So how do we make the phi go away? We can think of that as, okay, let's just go ahead and do a phi in the denominator. There it is, we got it. So that cancels, so we get x to the 4th. So the function that gave us x to the 4th, the antiderivative is x to the 5th over phi. Okay, so there it is, we have it. Okay, so I'm gonna go over the rule in a second, how we do this in general, but suppose that's our answer there. So we have 3 times, well, the antiderivative of x to the 4th is x to the 5th over phi plus c. So now we're just going to get 3/5 x to the 5th plus a bigger c. 3 times c is going to be bigger c. So that is the antiderivative function of 3x to the 4th. Now you may be thinking, do we have to do this every single time? Do we have to keep guessing and check which function works, which function doesn't work? Is there a rule for this? Well, it turns out the answer is yes. Just like the rules that we learn when we differentiate a certain function. With polynomial, we use power rule. With e to the x, we use e to the x. With natural log, we use the derivative rules for natural log. Antiderivative is just the reverse process of that. So here are our rules for this lesson here. So we say that, all right, so we said antiderivative, I always spell this word wrong, derivative rules for indefinite integral. And I would suggest you write these rules on your note card for this chapter. This is where you first start your note card here, is write down these rules. So this section we have 3 rules. We have the first one, we're saying that if we have the indefinite integral of some function that is in the form of x to the n, where n is some power, times dx, then the antiderivative of this is just the reverse process of differentiation. So we need to take that power, add it by 1, and divide by that power, and then plus c. Okay, so that is given that n is not equal to 1. So that is the antiderivative rule for functions or integrands, the function inside the integral, in the form of polynomials. Okay, so second rule. All right. If the integrand function is e to the x, then there isn't much for us to do. It's just the antiderivative, which is e to the x. So this is probably the easiest rule for us to remember. The third rule for antiderivative, what if we have 1 over x dx? Well, remember, natural log function, when you take the derivative of natural log function, you get 1 over the, you do 1 over the argument inside the natural log. So to reverse that process, we're just going to get natural log here for the antiderivative. But it turns out it's not as that simple, because when we do this here, we got to make sure that these functions are equivalent in both domains and both the domains for each function has to be equivalent. So it turns out that the domain for 1 over x is negative infinity to 0 and 0 to positive infinity. And then the domain for natural log of x only go from 0 to infinity. So it won't be equivalent in that sense. So to make it equivalent, to make sure that this is the correct antiderivative for 1 of x, we got to make sure that natural log of x needs to be defined on both interval negative infinity to 0 and 0 to positive infinity. So the antiderivative of 1 over x is not just natural log of x, but it turns out to be the absolute, the natural log of the absolute value of x. So this here, to ensure that, you know, we take the domain of 1 over x into consideration, right? Because the domain of 1 over x, so that domain is negative infinity to, negative infinity to 0 and 0 to positive infinity. So by putting the absolute value of x there, now the natural log of x defined for both intervals, negative infinity to positive infinity. And it turns out the graph looks something like this here. So the graph of natural log of absolute value of x looks something like this here. Is going to be something like that and something like that. So this is ln of natural log of x. Okay, so those are the 3 rules you need to know for this lesson, and it's going to help you a lot in the next couple lessons as well. So I would suggest make a note card for this here. So we have just enough time to do a couple more examples here. So I'll do one more example with the radical. Okay. Actually, I'm gonna go ahead and end the video here, and the next video I'll do 7 more examples.